side of a lithium cell,
Yeah,
like this,
excellent.
it would have a positive electrode, and it's made of aluminium. Yeah, I apologize to Americans who want it as spelled as aluminium. And then it's got a separator. And on the aluminium foil, it's got a coating, a sort of graphite type coating. And the other side, the negative electrode, has a copper electrode, which is universal between America and Britain, and it's got a graphite type coating on it as well. And what actually happens in lithium cells, it's a common misconception that the reason they're so volatile and they explode so regularly, they don't actually explode that regularly. That's just a media thing. The reason for that is because the reason when they do explode is because you get a dead short circuit between positive and negative. That suddenly unleashes all the energy. But the common misconception is that it's because it's got lithium in it. But in reality, it's got an aluminium electrode with a graphite type coating, it's got a copper electrode with a graphite type coating, and it's got a very small diffusion of lithium salts. And the lithium is, there's so, it's just a tiny amount of lithium in these cells. It's not that's the problem. The reason they grow nuclear when they get shorted out is because of the huge amount of energy. They're fantastic. They're a really amazing cell technology. So what actually happens is if you discharge this down to zero, there's some research done. If you search my videos for the word lithium, I'll put it in there below. That's the best bet. You'll find another slightly bootleg video recorded elsewhere where I really scoured the internet for research on lithium discharge levels. And it turns out you can actually discharge a lithium cell down to 0 volts without any real major issue. And what happens when you discharge it to that low level is that most of the lithium control chips, I've got my explosion containment pie dish here for a very good reason. I'm going to be taking out these. But let's find actually, I'm just going to be honest, see, seriously, before I started thinking this through, I should have looked for these things now. So let's plug this into a lithium power bank. So we got a nice 5 volt supply. Let's grab the little and let's see how much current it charges at. I'll just reset that. So what should happen is if the lithium cell is being over-discharged, the protection of the charging chip should go into a sort of safety mode and gently ease it back into the world of reality. So what's actually happening here is 100 milliamps. It's gently nudging it back up to 100 milliamps here. Let me just zoom in and show you that. 100 milliamps. That's not super in focus, is it? Let's focus down to is that any better? Yeah, it's kind of better. So it's trickle charging at about 100 milliamps, and as soon as the voltage in the cell reaches about 2.5 to 3 volts, which is considered acceptable, it will then kick into full charge mode, and the current will suddenly go up to about 500 milliamps. Oh, it's better. It's just gone up to 1 amp. Let's measure the voltage. Hey, where's the meter? What voltage did it deem was acceptable? Yep, the LED started flashing now because it's quite happy to charge it at that. And the voltage is, as soon as it's gone above about 3 volts, it's deemed that, it's at a level that it can charge properly at the full current. That's good to know. These power supplies, these little power banks, are very good just for taking the cell out of this typical power cell.
Come on, Marones. I want to leave it running.
And you get the circuitry next to it. The one downside of the circuitry in these boards is it's got a fairly high standby current, which is not so great, but still finding this application. Right, so what I found out before, let's focus back down this again. Let's make sure I have focused down that. Yes, I have focused down on that. What I found out before is if you discharge lithium cells to about 0 volts, it's fine. Usually, as long as you're recovering slowly at the sudden current, they'll just reform effectively. Everything will just sort of settle back down, and they'll take a charge, and if anything, they might lose a tiny percentage of charge, but it's capability, but it's not significant. But where a problem really occurs is if you have lots of cells in a series. Now, here is the equivalent of 3 cells in a series. Let's just give it a random load. Let's connect it to a random load like a resistor and an LED. So there's the LED being lit by 3 lithium cells, and initially starts off fully charged, but this lithium cell here has a slightly lower capacity. It's only just a few milliamp lower capacity, or in this case it was probably a bit more. But anyway, it starts off roughly about 7 volts average across these, currents flowing through the LED, and it's going from positive to negative. Now, I have to say this is where I have to differentiate between traditional current flow, conventional current flow, which is from positive to negative. In reality, the electrons flow from negative to positive, but that just confuses matters. The theory of electricity is based on electricity flowing from positive to negative. So what happens is the current's flowing through this, we're getting about 3.7 volts, and then we're getting another 3.7 volts, another 3.7 volts, makes up the 11 volts or so, and LED lights. But then this one is flat, so it's at 0 volts, and suddenly it's in a series of a circuit where that's positive, and it's pushing current through, and it starts reverse charging that cell. Now, this used to be an issue with power tools, the cordless power tools, the nickel cadmium power tools, the earliest ones. And they used to say the best thing to do is discharge the battery completely before you recharge it to avoid the memory effect. But in reality, some people did things like they put rubber bands or cable ties or tape around the trigger and let their cordless drill run completely flat. That's a terrible idea, because the first cell in a cordless drill that goes, battery pack that goes flat, then starts getting reverse charged, and it actually causes a slight bit of damage to it. And in future, when you recharge it again, because it's now been slightly damaged and it's got lower capacity, then the battery will run out sooner, and that'll then get reverse charged furthermore. And it causes an avalanche effect that over time, every time you charge and run it to completely flat, it actually damages that battery more. But it's worse in the case of lithium cells, and that's why in this case the battery pack quite justifiably rejected it. It probably tried charging it, realised it wasn't going to come back, and condemned it, which is quite acceptable in this instance, because what actually happens is if you discharge it to 0, that's fine, but if you start reverse charging it, so you get a higher positive voltage on the negative electrode and the negative voltage on the positive electrode, once you go above a certain level, and the scientists involved reckon that was about 12% of the charge. If you was to work it out scientifically and say the galvanic voltage differences between copper and aluminium, because that's what comes into play here, then what you end up is you end up with an electroplating effect when it reaches about, I guess, 2 volts, which is the combined electron difference between aluminium and copper. And what happens then is the copper ions, the lithium has already gone across to the positive electrode where it sits and just in storage until you charge again. But if you over-discharge it to the point that the copper starts migrating across, then that is a problem, because instead of just the lithium ions diffusing through this medium here, you end up with metallic copper from this foil actually travelling across and creating, it gets lodged in that membrane, and it creates a conductive trail through that membrane, and that then effectively is a resistance. And whereas the lithium cell that in the power bank was quite happy to take up a charge again, these ones are, let me demonstrate with a cheap current meter, a bench power supply, and we'll try and put a charge into these and see what happens. So let's bring in our big display meter. Let's put that down to about 200 volts. Let's get a setup rate. Misplaced. Am I misplaced those? Yes, I have. That's quite annoying. I did put those ones out before, and I've lost them. So let's get some croc clips into here. And let's turn the bench power supply on. I've limited the current to about 100 milliamps. Okay. So we'll connect the positive to the positive end of the cell, and the negative end, the negative charge lead, is going to go via the meter. So we're going to measure the current flowing, and we're also going to measure the voltage. This is going to get messy. Not to worry. We'll sort it out. So here's a positive. That's set to 20 volts. Let's start with this cell, which is showing 0 volts at the moment. Let's start charging it through that meter.
I'm gonna chat and stuff. I still very high up.
Oh, that's it. Not going too well. Rag of metal there. Activate the bench power supply. So it's showing about 100 milliamps, and the voltage across the cell should theoretically have started climbing, but it's not. That's not good. It should have notably started climbing at a significant rate. Okay, so let's change this to the 10 amp setting. And bump the current up a bit then. So now, I'm going to bump it up to about, let's monitor on that meter. I don't need to look at the bench power supply. So let's bump it up to about half an amp.